All right, so we're jumping into chapter 15, 15.1. Vector fields. So in chapter 12, we talked about vector valued functions. And a vector valued function, for a vector valued function, we assigned a vector to a real number. So we had a parameter. Often we had t as our parameter. So we assigned a vector to some specific time t. So like a position, a velocity, acceleration, something like that. So a vector valued function assigns a vector to a real number. Vector fields assign a vector to a point in space. So that's the distinction. So our input for a vector field, excuse me. So our input for a vector field is going to be a point in space, and then our output is going to be a vector for that assigned to that particular point. So our notation in the plane, we say, often we're going to use capital F. We'll say f of x, y, and we say that's m I hat plus n j hat, and m and n are both functions of x and y. We're assigning a vector to this point in the plane. And similar notation for vectors in space. So if we have a three-dimensional vector, our notation is going to be m I n j hat plus p k hat. And m, n, and p are all functions of x, y, and z. So examples of a vector field would be a velocity field, and you see those in fluids. So at a point in the fluid, you have a velocity vector. So at every point in the fluid, you have some different velocity vector. Gravitational field is a vector field. For every point in space, you have a vector that points in a specific direction that's describing the gravitational field, or electrical field. So if you have an electrical field, you have a vector that's assigned to every point in space for an electrical field. So those are examples of vector fields. Something that we've worked with quite a bit in chapter 13 that is also a vector field is the gradient. And that's going to be an important, we're going to use the gradient quite a bit in this chapter. So if we have some scalar function, we said that del f, if we have a function of x, y, and z, is the partial with respect to I, partial with respect to x times I hat, partial with respect to y, times j hat, partial with respect to z times k hat. So the gradient's a vector field. F sub x, f sub y, and f sub z are functions of x, y, and z, and we get this vector at any point in space. So if we think back to what we did with the gradient, the normal vector to a surface, at any point on the surface we get a normal vector given by our gradient if we had f of x, y, z as a constant. So that the normal vector, we could think of that as a vector field. We're assigning a vector to every point on that surface. If we're given some specific vector field, some representation of a vector field. We can sketch it or visualize it. We could plug in values for x, y, and z and get an idea of what it looks like. But there are some shortcuts that can help us do that. One shortcut that we can use is like we did when we talked about level curves, where we look where the magnitude is constant. So for a level curve, we set our function to a constant. We looked where the function was constant. So that's one way we can visualize a vector field, is look where the magnitude of the vector, the specific vector that we have, is constant. So what I want to do next is look at some vector fields and match them with some graphs. So I have some graphs here. I'm just going to grab those. Whoops. All right, so there are my graphs, and we want to match these to some vector fields. So the first one we're going to look at is, and we're just looking in the plane here, f of xy equals xj hat. We want to figure out which one of these vector fields matches, which one of these graphs matches this vector field. So the way I would look at this one is I would say, all right, so for every x value, I have a constant magnitude in the y direction. And as x increases, the magnitude gets bigger. As x decreases, the magnitude gets larger, negative. So Griff says C. So constant magnitude for any specific value of x in the y direction only. So this would be C. So the next one. Next one we're going to look at is, and this one, if we got that one, this next one should be pretty easy. We're looking at y I hat. This is a y, not an x. So what do we think? D. So for any specific y value, we have a constant magnitude, and our vector only points in the x direction. Positive above the x-axis, negative below the x-axis. So that would be D. So those two are pretty easy. Let's look at our vector field xy is x I plus 3yj. We want to match that one. So let's look at where, my suggestion was, let's look at where the magnitude is constant. So the magnitude, what's the magnitude of this vector? X squared plus 9y squared, and that equals a constant. Square both sides, so I get x squared plus 9y squared, some other constant. So what's the graph of this look like? This is an ellipse. So our magnitude is constant on an ellipse. If I divide everything by 9, I would see that my major axis is along the x-axis. So that would have to be B. So we looked at where the magnitude was constant. Next one, f of xy, our vector field, is yi minus xj. Who said E? Griff says E. And what makes you say E? How did you think about it?
Well, so I look at C, and I figured that if it was going up, I mean, if it went in the same direction as the sign that was the half up, so there's maybe a positive X.
Okay.
If it switched, then it had to be the opposite.
Okay. So you just thought about specific values of X and Y and how they would have to, how the field would have to change. So that would work. Another way you could do it is we could look at the where the magnitude is constant. So you could you could plug in values of X and Y and say how does it behave, and that's fine. And we can see here that I think what Griff was saying is as Y increases, the magnitude in the X direction increases. So as Y increases, the magnitude in the X direction is getting bigger. As X increases, the magnitude in the Y direction is getting larger, negative. So if we look at the constant magnitude, the magnitude of this vector, square root of y squared plus x squared, is a constant, or x squared plus y squared is some other constant. So we have a constant magnitude on circles. And if we go around the circle, the vectors here have a constant magnitude. The vectors in the next circle have a constant magnitude. So this would be E. So we've eliminated quite a few of them. The next one we're looking at is our vector field is xi plus sine y j hat. This one's a little, I have to think about this one a little differently. Any ideas? It's either F or A, right?
A.
So what do you think A, Sean?
Well, even ignoring the sine y, I know as it increases in the x direction, the magnitude has to increase
Right.
towards the x, and I see that happening in A and not in F.
Okay, that's so what Sean said was as we move in the positive x direction, that magnitude in the x direction has to increase. So if we're moving in the positive x direction, that's happening here. That's not happening here. The other thing that you could look at is say that the magnitude in the y direction only varies between positive and negative 1. So it goes up a little bit, so it has to go between negative 1 and 0. And that's what's happening here for the y component. And then I'll just write out, so we already know that is A. So the only one left is F. And the vector field that we have matched to match F is 1/2 xy and 1/4 x squared for the y component. And the way I looked at this one is kind of similar to the way Sean did the last one, is I said the y component always has to be greater than 0. Greater than or equal to 0. So the y component's greater than or equal to 0. It's never negative. So that's the way I would look at that one. So that's, yeah. The y component is always positive. They're always pointing up or horizontal. All right. Questions on those? So just a little work with visualizing these vector fields. All right. So there's several things that are going to be important about vector fields, and that certain kinds of vector fields are more interesting and more useful and have more interesting properties than others. And one of those types of vector fields, probably the most important kind, is a conservative vector field. And when we get further into the chapter, conservative vector fields have some really nice things that make our problems easier to solve. And we'll talk. We'll have to do this a lot in this chapter, where we put off what things mean until later, until we understand a little more. So we're going to talk a little later about what conservative vector fields conserve. So our definition of a conservative vector field. If our vector field f is the gradient of some scalar function, so f has to be differentiable, then we call our vector field conservative. So if our vector field, if we can find some scalar function, small f, such that our vector field is the gradient of that function, then we call our vector field conservative. And we call f, small f, our scalar function, is called the potential function. And a lot of this terminology, if you're in physics or if you've taken physics, this terminology is going to be very, very familiar. Same kind of terminology that you use in fixed physics for these kinds of things. And what we're doing in chapter 15 kind of developed right around the same time that the theory of electromagnetism was developing. So mathematicians, physicists were trying to develop these tools to work with electromagnetism. So we end up with using the same terminology in math and in physics. So if our vector field f is conservative, it's the gradient of some scalar function, we call that scalar function the potential function. And just a reminder that the gradient of a scalar function is normal to level curves, and it's normal to level surfaces if we have f of x, y, z is a constant. So that's going to be important also. So an example, let's just look at a couple of, a quick example with a vector field. If your problem asked you to ask you if we have the scalar function and we want to find a conservative vector field for this potential function. Our vector field, so this should be an easy problem. Our vector field is just the gradient of our scalar function. So the problem asks you to find a conservative vector field, we just take the gradient of the function. So f is the capital F, is the conservative field. And f, small f, is the potential function. So questions on that one? That one should be, we just want to find a conservative vector field, we just find the gradient of our scalar function. So later on it's going to be important to decide whether or not our field is conservative. We want to, if we have some vector field, we want to decide, is it conservative? Is it a conservative field? So we want to figure out how we test for that. Well, luckily we have a nice way to test, because our gradient has to do with partial derivatives. We have a test that has to do with partial derivatives. And right now we're in the plane. We'll talk about in space in just a minute. So our test for conservative fields in the plane. So if we have a vector field, f of x, y, and this is mi plus nj, and we know, so we want to decide if this is conservative. Our theorem is this is conservative if and only if dm dy, partial of m with respect to y, equals dn dx, partial of n with respect to x. And our assumption is we're dealing with nice functions. So m and n have continuous first partials in some area of the plane. Anybody have an idea why this would tell us that this is a conservative vector field? Thinking back to what we did in chapter 13 with partial derivatives.
Is it because the like f of x, y, same as f of y, x?
That's exactly why. The second mixed partials, if we have a nice function, our mixed partials are equal. So if f is conservative, then we know that f is the gradient of some scalar function. So this is our conservative field. So that tells us that m equals df dx, and n is a partial of f with respect to y. And my mixed partials, I'm going to use a different terminology. So fxy is dm dy, and fyx is dn dx. And our mixed partials are equal. We have a nice function, our mixed partials are equal. So this is our test for conservative vector fields in the plane. If we have our vector field represented this way, we take the partial of m with respect to y, partial of n with respect to x, and see if it is equal. And this lets us, if we have a conservative field, it lets us find the potential function. So let's look at how we do that. So any questions before we move on? All right, so here's our example. We want to know, is the field conservative? And if so, find a potential function. So here's our field. Our field is 3x squared, y squared, I, plus 2x to the third, y, j. So in the terminology we've been using, that's m and that's n. So our test, we want to take the partial of m with respect to y and the partial of n with respect to x and see if they're equal. So dm dy, our partial of m with respect to y is what? 6x squared y. And our partial of n with respect to x is 6x squared y. So our answer is that it is conservative. Now we want to find our potential function. So we need f of xy, some scalar function f of xy, so that the gradient of our scalar function is our vector field. So this tells us that df dx, the partial of our function with respect to x, has to equal 3x squared y squared, and the partial of our scalar function with respect to y has to equal 2x cubed y. So what we have here is two differential equations that we can solve simultaneously. So f has to equal the integral of 3x squared y dx. If I take the integral of that with respect to x, is it y squared, 3x squared y squared? And when I take the integral of that with respect to x, I get x cubed y squared. Now we have to be a little bit careful here. We're taking the integral with respect to x. Our constant of integration could be some function of y. So I'm just going to write plus g of y. And when we solve our other differential equation, we have to look at our constants of integration and see if we need to adjust. Because we're integrating with respect to x, our constant of integration could be a function of y. And f also has to equal the integral of 2x cubed y dy. And when we integrate that with respect to y, we get x cubed y squared plus some h of x, some constant function. Our constant of integration could be a function of x. Well, if I take the partial derivatives of each of these, I get my scalar function. So I don't need to adjust with my constants of integration. I would have to adjust my constant of integration if I took the partial of this with respect to x and the partial of that with respect to y, and my function was off by some function of x or function of y. Then I would have to adjust. So here we're all set. Everything's good. So our potential function is just x cubed y squared plus some scalar constant. So that's our potential function. That's our potential function. That gives us our conservative vector field here. Questions on that example? All right. So the next thing we're going to do is move into space. Move off the plane and into space. And we get this nice new idea about that we can use with vectors. And a new term. We get to use a new term. The curl. And the curl is something, one of those terms that, like I mentioned before, that we're going to have to talk about and work with. And it won't be until the very end of the chapter that we can give a really good interpretation to what the curl means. We can talk about an idea about what it means, but it's going to take until the end of the chapter so we can get a firm grasp on what the curl is.
How many steps in this chapter?
8. 8 sections we have in, what do we have, 36 days left?
Well, we only have 22 days of school.
So 22 days. So that's 8 sections, 22 days.
That's 18 cents, we're practically not here.
Right, right. That's, so we're,
Is there a Colorado Math League in there?
no, Colorado Math League's over.
What about the Southwest?
The Southwest Math League. All right, so the curl. So if we have, we're going to define our curl. So we have a vector field in space. So this is our vector field. The curl of f, and we write the curl several different ways. We can write curl of f is going to be del cross f. So we're using our del as a differential operator. So remember that we said that del is d dxi plus d dyj plus d dz. Okay. Now all we've done with del so far is operate on a scalar function to find our gradient. Well, now we're using del and we're using vector operations. We're thinking of this as a vector operator. We're using vector operations with del. So del cross f, the way we calculate del cross f is with our determinant, just like we do a normal cross product. We would do I, j, k, d dx, d dy, d dz, m, n, and p. So that's how we calculate our curl. If we write this out, if we write it out term by term, and you'll see it written out term by term sometimes, this equals the partial of p with respect to y. It's kind of a long thing, minus the partial of n, and it's just evaluating this. That's our I component of our curl, minus, and here's our j component, plus, and our k component of our curl, and that's just this all written out. And you'll see this written out sometimes as well. So this is our curl. We say that if the curl is 0, our field is irrotational. So if our curl is 0, our field is irrotational. And a vector field with a curl of 0 has
What does that mean?
Yeah.
Can't rotate it.
and like I said, it really takes to the end of the chapter to give a good definition of what the curl is. But the curl tells us the tendency of the vector field to cause a rotation. So if the curl is 0, that vector field doesn't cause a rotation. Is in very broad terms what we're talking about. And once we get into using the curl a little more, we'll have a better idea of why that is.
What does it mean to do in a cross product?
Then the vectors are parallel.
Parallel.
Parallel. All right. Let's do a quick, I'm just going to do a quick example of setting up and finding the curl. Finding the curl is not difficult. It's more what we do with the curl that's interesting. But we'll end up having to find the curl often in this chapter. So we want to find the curl of our vector field. X squared z I hat minus 2xz j hat plus yz k hat. So we want to find the curl. So I'm just going to form del cross f. And put my components in here. And form that determinant. And when I calculate that out, now the mistake, the one place that a lot of people make mistakes with cross products, you make a sign error when forming this cross product. So be careful, make sure you get the j component negative, and make sure you get your pluses and minuses when you form your individual, your 2 by 2 determinants. It's really easy to make a sign error. So that's one place to pay really close attention. If I carry this out, I end up with 2x plus z I hat plus x squared j hat minus 2z k hat. And then if I needed the curl at a specific point, I could just plug x, y, and z into that.
So you're basically multiply.
Right, when I multiply, rather than multiplying, I'm taking the partial, I'm doing that derivative. So with this first one, I would do the partial with respect to y of yz. And that's where I got the z, right. Does that make sense? So rather than multiplying, we're doing the derivatives that the 2x to partial with respect to z here. All right. Did I make a sign error, Liam? Oh, what?
With respect to x and y,
X squared, yeah, x squared z. So that's where the x squared comes from. And it's good to go back and double check, because that's in that process, that's where people make mistakes finding the curl. And if our curl is 0, we call our vector field irrotational. Well, the curl being 0 tells us something else about our vector field. So we had a test for conservative vector fields in the plane. So now we need to talk about our test for conservative fields in space. So our vector field F, and we're in space now, x, y, z, and we're using our same notation. Is conservative if and only if. What are you going to guess? Anybody have a guess how we tell if a field is conservative in space? Same with the last, but with a z component. And what would that give us? What's that? They're not all 6 equal to each other. Our field is conservative if and only if del cross F equals 0. And you were thinking in the right track with those partials. This is equivalent to dp, the partial of p, with respect to y, equals a partial of n with respect to z. The partial of p with respect to x is a partial of m with respect to z. And the partial of n with respect to x is the partial of m with respect to y. So there was what we had in the plane. So the curl being 0 is equivalent to these conditions, and these are exactly the same as saying that our mixed partials are equal. And if our field is conservative, we can find the potential function just like we did in our last example, except we have 3 equations that we have to integrate to find our potential function. So if our curl is 0, the curl is 0, our field is conservative. That's the same as saying the vector field is irrotational. The vector field is irrotational. It's conservative. So all those are saying the same thing. So this is our test for a conservative field in space. Questions so far? Covered a lot of ground, talked about a lot of new things. Nothing real complicated, we're just applying ideas that we've already used in slightly different ways. So the next part I'm going to leave up to you. We can do an example of testing for a conservative vector field in space and then finding the potential function. It's essentially the same as the last example we did. If you guys are feel okay with this stuff, we can not do it. Want to do it?
No.
All right. So our question is F conservative? And if so, find a potential function. So here's our field. Stick with me, guys. So there's our field. So we're going to form the cross product. Find the curl, del cross F. So we're going to form that cross product. And when we form that cross product, I'm not going to go through the calculations. It turns out that when we form this cross product, that each component does in fact equal 0. So when we take these partials and subtract, we get 0 for each component. So now we want to find, this tells us that F is conservative. The curl is 0, so F is conservative. That tells us that if our potential function F potential function is f. So the partial of f with respect to x is y squared z. So the integral of y squared z dx is x actually I wrote I missed a cubed here. This should be cubed. So I bet that first vector field would not be 0. Or they would not be conservative. All right, so this is my integral. I apologize. Told you I was not feeling well. I have a cold. So this is x y squared z cubed plus some function of some constant function potentially of y and z. My partial with respect to y is 2x yz cubed. The integral of 2x y z cubed dy is x y squared z cubed plus some constant, some function of x and z. Our constant could be a function of x and z, our constant of integration. And f sub z is 3x y squared z squared. So I integrate that with respect to z, 3x y squared z squared dz. And I get x y squared z cubed plus some function, constant function with respect to z of x and y. Well, if I take my gradient of this, I get my original function, so I don't have to adjust my constants of integration. So f is, my potential function is x y squared z cubed plus some constant.
Are we gonna ever have to adjust that?
In the homework problem, I think there's one question where you have to look at these constants to make sure that your gradient comes out correctly. So what you would do is, for example, if you took the partial of this with respect to x, and you didn't get y squared, if you didn't get y squared z cubed, you would need to adjust this, and you didn't get what your partial was, you'd have to adjust the function so that when you took the derivative of this with respect to x, that you would come out with that.
Could you just find what h y
Right, right. To make it work out. Yeah. So how would you end up with a function when you have a function that they have to adjust? Guys. Right. So if I took h of yz is constant with respect to x, so I could have some function of y and z that ends up in my as my function. So when I took the derivative of that, what's that? Okay, did that help at all? All right, homework.
No, not that. Took your homework.
You can't assign homework after class then.
All right, there you go.